Thanks for the invitation to talk to you today. And I think I want to put a very personal spin on some issues that have been touched on before. And one of the aspects that I really want to emphasize is the quality of the resource pipeline that we're dealing with. It's something that Richard mentioned in the last bit of his talk, but that you don't hear it a lot in the media about deposit quality. I mean, it's great that exploration is now getting a Guernsey in the media. For years, we didn't hear anything about exploration being a key driver of value or the need for exploration. But I think one of the key things that's been missing in it is this aspect of deposit quality. So this is an older slide from Richard, but it illustrates the point, and it shows copper projects around the world. And it shows them in their various stages, from exploration right through to closed. And the important envelopes to look at there are the envelope for economic mines and the envelope for undeveloped projects. And the key thing is that a lot of these projects are right on the line. Right? There's not a lot of quality projects sitting out there. And in fact, I would say that a lot of the money that has been put by majors into some very big projects, and we'll talk about the reasons why in a second, is really sitting in these marginal projects that are essentially stalled. So when you look at there's a number of studies that have come out in the last 5 years that have talked about the fact that, we've got a growing resource base, and then we've got resources in copper or gold or whatever for however long, because they're looking at taking current resources, dividing by current production rate, and saying, therefore, we have metal for this long. Where the reality is, and many of us intuitively understand that, is that a lot of these resources are effectively stranded. Right? They will never see the market in our lifetime, I would put to you. Right? And the result of that is that there's constantly an undercall between what industry is promising to the market versus what they're delivering to the market. And this graph shows the last decade or so, and it shows it with the interpreted causes on top of it. And if you take out things like weather and strikes, a lot of the rest of those factors actually sit in the bin that I would put largely as deposit quality. And the other thing that you get confronted by is people say, well, surely that this will be balanced by supply and demand, that there's basically the market pressures will come on, the prices will go up, and therefore all this metal that's sitting there now becomes economic, so surely that will fix it, right? And what history has shown us is that's not the case. Once you have a marginal deposit, barring some major technological breakthrough, and even then, right, a marginal deposit stays marginal. And this graph shows that schematically in showing pre-boom through a boom into a crash. And it shows two lines there. One is the commodity price in yellow, the other is the production cost, everything it takes to bring that metal to market in pink. And basically in the zones where the polygons that are shaded pink, you're losing money. The polygons shaded green, you're making money. So what happens through the cycle is that when metal prices come up, they appreciate much faster than your fixed production, your costs of production. And so these marginal deposits end up looking economic. And so people end up dusting them off, giving them a new name often, and bringing them out to market. The issue is that your production costs quickly, you remember that your production costs are essentially people, materials, and energy. Right? And those three things start to come up pretty quickly. Like I always use the example between 2003 and 2008, I say, how many geologists got a pay cut? Right? And the answer is not many. Right? People were walking out of university with a few field trips out in their hand, and they were making more than their lecturers, right, when they go out to work in the industry. They're poaching people out of third year. So try to buy a tire at that time. Right? So these costs quickly erode that margin, but then when the prices drop, they often drop fairly quickly again, and at that time, your fixed costs, they're in, they don't drop at the same time. So what happens? Mass retrenchment, projects shelved, and that's how our industry has managed cyclicity. Right? So the answer really is to get away from the marginal projects, right, and focus on quality of the resource base. There's a few other issues that I think are going to change in the future our industry, and I don't think these have really hit home as much as they need to with a lot of the industry, right up to the top management. So this is showing Antamina, which is one of the 10 largest mines in the world in terms of rock volume moved. In the future, these are the types of things that are going to be difficult to get going. Right? Number one, people don't like it. Right? So society doesn't like this sitting in their backyard. But I think more importantly from an economic point of view, and that goes to a social license aspect that we'll talk about in a second, but is that these things are very energy intensive, right? How much energy does our industry use, right? In Australia, we put as much money into crushing rock, just crushing rock in our industry, as the entire residential sector. In a population over 20 million, a country with a population of over 20 million people. That is a lot of power. Another rule of thumb, processing a ton of rock takes about a ton of water. Right? And this is an issue in Australia as well. So take that into the future. Take that thought experiment forward and say, in the future, we're moving into an energy-constrained future where energy is not only going to cost you more, but it's highly likely that some form of emissions tax is going to come in globally. Whether we agree with it or not is a totally separate issue. Right? Society's moving that way. It's rapidly moving into legislation. This will redefine what ore is for us. And then look at where the big projects are that are stalled and that has destroyed a lot of value over the last boom. They're large, low-grade, long life, right? But they're super high risk. Right? And as I say, I think a lot of these things are stalled for a long time, and Richard probably can, because he's looked into this in detail, he can probably comment on that more. So the idea is we have to focus on higher quality mineralization. That means more extractable metal per ton of rock, or more extractable metal per kilowatt hour, another measure you could use. So in our industry, there is what we could call a failure of agency. So when you look at the current industry practice, it's not in line with that future ore paradigm. So now that's not saying that there's a lot of smart, visionary people in the industry, right, and leading the industry. The problem is they keep getting beaten into a box by a lot of factors, right? So the external factors, like the equity markets we've been talking about, and internal factors. If you look at remuneration packages and KPIs, the higher you go up the food chain, the more it's tied to something that's quarterly, right, or annual at best. What does that do? It fosters short-term thinking, shorter-term results. It results in a focus on brownfields, right, which is fine, and we've all talked about that. There's a lot of option in brownfields, but the real value is in opening up new mineral districts that come with that expanded brownfields option value with them, right? So it's the fact that we're focusing on brownfields at the expense of greenfields. That's the problem. Majors trend away from exploration to acquisition. They focus on extraction technologies, productivity issues, all masking the underlying problem of declining project quality. There's the expectations that juniors will fill the greenfields gap. They just don't have the capital structures we've been talking about to undertake these types of longer-term programs required to open up new mineral districts. And we've already talked about the fact that metal prices won't sort out the supply. So all of those problems are fundamentally challenged into the future. So in any deposit, to get value out of a deposit, there's a number of different factors, and you can put them into below ground factors, which is largely pinned to geology, and above ground factors about how you can engineer that, how you can financially engineer that, social license to operate, etc. And this diagram just shows those linkages. So it's a complex system, and a high quality deposit navigates those to deliver value throughout the business cycle, right? And that's the key, not just in the good times, but throughout the business cycle. So if we think about how our industry generally manages, this is a diagram that was put together by John Sykes. It's got three axes. The bottom one is the below ground factors, right? The geological certainty increasing to the left. The back red one is the above ground factors we generally worry about, which is the engineering, the financial, and the physical and financial engineering of the project to make it economic. Then we tend to worry about, if we find a really high quality deposit, then we worry about, can we mine it? And in the future, with that, we were talking about that social license to operate. You know, at the moment, we look for financially optimal projects that are socially acceptable. And in the future, we'll probably have to start looking for socially optimal projects that are financially acceptable. I mean, it will be a fairly major switch potentially in our thinking. So a lot of projects don't sit in that green. What we've got to start doing is exploring in the light green box and moving it to the darker green box instead of moving it at the back and parking it in that big red box at the back. Okay. So that's what I've just said. And in fact, Robbie Rowe pointed this out about a year and a half ago, where he said he sees that in the future, major companies are going to abandon a lot of the developing nations and come back to tackle the technical challenge of exploring under challenging cover in developed nations. Right? So this could herald a return to Australia, given that we improve access issues, which was a comment that came up earlier. So, can we want to find high quality deposits, but can we actually explore for quality? Right? It's a problem because it's a complex system. So we actually now are at the point where we can map quality through an ore body and actually then start to predict ahead of mining where that quality ore chutes are, why they're there. Okay. And there's a really good paper in the AusIMM journal by Kathy Aragon on Olympic Dam where they do just that. Right? And the problem is, can we explore for it? And the problem, bringing it out of scale, is that one is technical. There's the inherent variability between ore bodies. No two ore bodies are the same, so how can you know if it's high quality or not in advance until you find it? Right? And then that's the one common belief. And the second one is that heuristics are a software problem because we're a discipline-based industry with very different software about how we look at the industry. And I'll talk about that. So, exploring for quality. So this diagram shows the problem schematically, and it shows the relative input of prediction versus detection technology from broad regional targeting through to the prospect scale. And the trade-off is that at the prospect scale, we've got a lot of detection technology that we can throw at a deposit where we can taste it, feel it, sample it, basically assay it. Whereas when we move out to the broad regional scale, there is no prediction technology. So, there is no detection technology. It's all about prediction. We're all in the predictive space. And the challenge is that camp scale decision where we're locking in to a strategy, a bit of ground, our costs go up, our flexibility goes down, and we're still largely in the predictive space. So we can detect quality now at this phase earlier, but can we predict it earlier on? So where do we focus that expensive detection technology? So again, the problem, just showing the Yilgar in various scales. How do you predict the location and the geometry of high-quality mineral districts or camps or ore chutes at the various scales? So there's a couple of advances that have come through in mineral systems, and one of them is understanding the rates at which these things form. So we've got to remember that when we look at ore deposits, we're seeing the fossil of a whole bunch of processes that integrated together to form that deposit. The real question is how fast were they going? How fast did those processes work? And the more precisely we can date mineralization events, the more we realize these are just lightning bolts in a much broader maelstrom of largely barren metamorphism, deformation, magnetism, fluid flow, etc. They go very quickly. Carlin trend, we now know, is 100 million ounces of gold sitting in less than 20,000, maybe as much as 40,000 years. Right? Not the millions of years we used to think of. So they're very, very quick systems. So they're dynamic, complex systems. And so one thing that has been coming out is understanding the dynamics of complex systems and being able to translate that into understanding ore deposits. And that's where I want to take you now and say, this is one way we might be able to come out of scale in terms of predicting where high-quality mineralization could be. So many natural systems show, despite a whole wide range of starting conditions, they show order, they show patterns. This is the opposite of chaos. You know, the butterfly flaps its wings in Peking and there's a hurricane off of New Orleans, right? Small changes in starting conditions, big changes at the end. We're talking the opposite. We're saying you can have a whole range of starting conditions, but we always see patterns. And these patterns are usually fractal in nature, and they show scale invariant power law behaviors. And the example that the physicists use for that is geological is the earthquakes. So just some examples. Richter scale on the bottom left-hand side. We know that there's 10 times more magnitude 4 earthquakes than magnitude 5 earthquakes. We know they release 10 times as much energy at magnitude 5 than magnitude 4, and they show that across a range of scales. That's why it's a power law scale. Fault sizes in oil fields from wells and seismic, again showing that power law relationship. And we see it with deposit size frequency distributions as well. And Pietro has a really good paper that Pietro Gui put together, a good paper in economic geology to show that over time in the Yilgarn for gold, for those interested. So this tendency of complex systems to order around a critical point is termed self-organized criticality. And there's some key aspects to self-organized critical systems. Number one is that you put energy into a system slowly over a long period of time. You put a barrier in place that stops that energy from dissipating into a sink. In doing so, you build up extreme energy and pressure gradients. As long as those conditions are kept in place, the system self-organizes, it transiently breaches that barrier, and then as long over very rapid pulses, and then when I destroy that situation, the whole system stops again. And so mineralization, I would argue, is also a self-organized critical system. We see that there are transient events in much longer periods of energy input, fluid input, multiple repeated pulses. They show the scale invariant power law distribution. They're fractal in geometry, all these attributes. So the diagram at the bottom left, or at the left, sorry, shows just the general concept of a self-organized system with the energy source being put in slowly, the threshold barrier being put in place, the system self-organizes, and you get these transient breaches across that barrier, and ore forms in the exit conduits. On the right-hand side, we've put that into a diagram that looks more like a mineral system. And the important thing about that, it also looks at what process in the whole mineral system are you going to be trying to map at what scale. So if you're looking at a regional scale, you're not worried about sites of deposition because it actually doesn't matter. You're worried about how do you put a lot of mass and energy through a small volume of rock. When you're at the deposit scale, you're no longer worried about the regional situation. You're worried about where are the exit conduits that form the high quality ore. So the general idea being that you can have an origin happening with lots of metamorphism, deformation, fluid flow, all happening. You're getting broad halos, anomalous metals, enough smoke that you don't want to walk away, but you're not getting high quality ore. You put it to a situation where the system self-organizes, you form the high quality ore, and then after you destroy that situation, you go back to your general background, just anomalous metals, a lot of smoke that you could waste money on. So the question is, that central bit, how do we recognize that high quality ore, and how do we map it by proxy in various data sets at various scales? So I'm just going to give you an example from the Andes, but these are some advances that have really come across in mineral systems that impact on how we will target for these high quality systems. So number one, the understanding that mineral systems are dynamic, complex systems that exhibit this self-organized criticality. The second thing is that diagram at the bottom, that to form a high quality mineral deposit, you need the conjunction of fertility, of the availability of metals in a geological time period or spatial location, favorable whole lithosphere architecture for the mass and energy transfer, and favorable transient geodynamic triggers that set up the self-organized critical system, the extreme energy and pressure gradients. In application of the mineral system, the key thing is whenever you hear people argue about what they need to target for, they're usually talking across scales. Right? So that somebody's talking deposit scale when they should be thinking regional scale, or somebody's talking regional scale when they should be talking deposit scale. So, in the Andes, as an example. So the Andes has been a compressional margin for a few hundred million years or more. It's so should be favorable for ore deposition. But the highest quality copper events have all happened after 100 million years ago. Right? So why is that? Well, around that time, the southern Atlantic Ocean started to spread faster. What that did was it pushed South America harder to the west. At the same time, the Ongtong Java Plateau comes out in the middle of the South Pacific, pushing the Pacific plate harder to the east. And that makes that whole margin anomalously compressional. The maximum amount of subduction below 20 degrees is all on that Andean margin. Right? It's an anomalously compressional margin. But within that, that's not enough. There's been moments where we've had anomalous compression on top of that. And an example is in the top left, that Nazca Ridge obliquely subducting under the margin of South America. As it obliquely subducts, you can see above it, there's ore deposits, and the volcanoes, the stars, have stopped. Volcanism shuts off, you form ore deposits. Why? Because you've clamped vertical permeability. You're choking the subduction zone, you put the crust under compression, you form the high quality ore. As soon as the Nazca Ridge keeps moving on, the volcanoes come back and the ore formation stops. So an example of that self-organized critical system controlling the camp. And then when you get down to the deposit scale, the example of El Teniente, these stalks that we know are less than 500 meters in diameter generally, and they're the constant exit conduits for these fluids coming from depth. So the idea is being able to map at various scales aspects of the system. So let's just back to that. So essentially that's what the Uncover vision is about how to align mineral exploration geoscience at a range of scales to help us unlock new mineral districts. And at the moment, that's undergoing a road mapping exercise through Amara, led by Robbie, who's in the room. You should ask him about it. And it'll be released later this month. And that's informing all of the federal initiatives from the survey point of view in terms of data collection, product delivery, etc. I just want to finish on a couple points of making this happen and the need for boundary spanners to make the connections. The great thing about people in this room here is we've got people that come from mining geology background, a lot from an exploration background, and some from a mineral finance background. And in a lot of cases, these don't mix. You're aware of this, those who work on sites, we're often engineering and geologists. Not only they're often physically separated, and even when they're brought together, they have a different software. They've been programmed, same hardware, different software. They've been programmed to look at things very differently. Boundary spanners are people that actually can link across these disciplines. And they're the type of people we need to identify and nurture in our industry. So there's two types. There's inside outsiders, right? These are people who are outside a community, look inside and say, I think there's a different way you could do that, and they bring in an idea into that community. And they're often rejected because they're not a local. They're not from our tribe, right? Therefore, you tend to dismiss their arguments. The outside insiders are individuals that sit within a community but can see something that sits outside that discipline and pull it in. That generally gets more accepted because they're one of the team already. Just some examples. So many of you might be aware of heuristics and biases. Daniel Kahneman, with his partner Ernest Tversky, were the people that put this stuff together in the 60s and 70s. But he was an inside-outsider when he started to talk about this drove economic behavior. And so he was met with a lot of resistance until he met an outside insider, Richard Thaler, who was inside the economic community, recognized the importance of heuristics and biases, and they together created the new discipline of behavioral economics, and they won the Kahneman won the Nobel Prize for this. Closer to home, people like Alfred Wegener postulated continental drift, and geoscientists much maligned it. They had a special conference in the late 1920s specifically to say why continental drift couldn't work. Right? That's how bad it was. Right? And then Arthur Holmes, right, was a geoscientist who was looking at the thermal implications of mantle convection. He saw the implications of the continental drift theory and put a process behind the empirical observation which led to the eventual acceptance of plate tectonics. So, in our industry, we've got two domains of thinking that we generally have to deal with. One is the exploration domain, and one is the project development domain. In the exploration domain, where we have to focus on the interface, is marrying all the fundamental science and traditional economic geology ore deposit studies that we do on the left-hand side with the actual business of mineral exploration and mineral economics on the right-hand side. The only way to do that is to understand mineral systems and understand how we can translate that to practical targeting systems. So we have to build people across that interface. In the project development domain, you've got the same challenge, is that ability to marry the fundamental science and engineering studies on the left-hand side of the diagram with the realizing a value in a deposit on the right-hand side. And that's through that diagram I showed earlier, the whole value chain of mineral deposits. And then, ideally, being able to find boundary spanners across those two domains so that we can say, this is what makes a high-value deposit, and then this is how we can then explore for it. So I'll leave it at that because of the time constraint. John? Oh.
Thank you, Cam. You all got some real geology in there as well, I noticed that. Good and fast one. Have we got any questions for Cam? Julian, yeah.
You talked about boundary spanners, but earlier on, despite the fact that you come from a university, you hardly mentioned students or education. Is this the concept that the next generation of students that come out will be boundary spanners?
That's the idea, is that you want to be building people that can move across it. For example, look at John, right? John sits actually in Curtin Graduate School of Business, but is trained as a geologist, right? Linking across that boundary. So he's a good example, trying to marry geoscience with the mineral economics side of things. So yeah, that's the idea, is that you want to immerse students in an area where they're interfacing across those boundaries with other people.
And at what level is that? Is that the PhD level?
PhD, postdoc, yeah, you're immersing them in that whole environment, yeah. I mean, no one study, right, can look across all of that. But many of our studies have, multiple institutions, multiple people, like the Capricorn Initiative, where they're dealing with people right from geophysics through to economic geology, and then in some cases through to mineral economics.
So what is the future for geology education?
I think the future for geology education is looking at things from a systems approach. So getting away from just the taxonomical, here's another documentation of a deposit, right? And saying, here's the fundamental questions we don't understand in why we see patterns in empirical data sets. Therefore, we need to go document these deposits with these particular questions in mind. It's a very different way of approaching the problem, right? Rather than just doing your standard cookbook documentation, you're actually about saying, this has a piece of the puzzle that'll help me understand the overall system. So it's this complex systems thinking in geology, I think, is the key change. Rather than taking another bird, stuffing it, and another finch that you put on the shelf kind of thing. Exactly the way the medical profession's gone. The medical profession used to throw a person out in the 1800s with an anatomy degree, and they'd learn on the job, trial and error. And used to do medical diagnosis based on empirical patterns and race patterns, etc. Right? Whereas now, we map the genome and we can tell whether one of you is going to be more prone to a disease than another, not based on the empirical pattern, but based on the fact that we actually understand the process behind it.
Sorry, Lisa's got a question first, and
Yeah.
then.
I'm interested that you finished on the concept of understanding process. Do you think that your ideas around self-organized critical systems are more susceptible to getting the right answer for the wrong reason? And are you also looking at how you demonstrate that your success, for example, in target quality, that you got the right answer for the right reason?
Absolutely. The self-organized critical systems is one aspect I just brought out as a change of way you can change your thinking, right? But you're right. What we tend to do is we tend to find empirical patterns in data, and we're much more confident with empirical patterns in data. But we only really have good confidence in putting a lot of money behind those if we understand the underlying process, right? So I think marrying the empirical science and trying to understand the processes behind it is key. Same with the financial world. That's why finance leans so heavily on trends, because it's so complex, no one has the process understanding yet, except after the fact, right? Which doesn't help us, right? So with self-organized critical systems, what that's brought understanding around is things like the power law size frequency distributions that we see in deposits, right? That's something that's always been black box, for example, where people have said, well, I'm not sure they exist, and it's like you have incomplete data. But now we realize that they should exist. They should show self-organized critical behavior. They should show these power law relationships, right? So that's an example where you're putting a process behind what before has been an empirical pattern that people weren't comfortable with because it was just empirical.
One final question, and then we'll move on.
Cam, what about what could we learn from the petroleum industry that fits into your thinking about predictive science, value chains,
Well,
and downstream?
I mean, we ripped off mineral systems from petroleum, right? So petroleum went that way in the late 70s, and maybe even started a bit earlier, but really took on in force in the late 70s, early 80s, where they started to take a systems approach to what type of critical elements need to line up to make a big petroleum concentration. And in fact, they went into things like the size frequency distribution. The challenge we had, that started to come on in the 90s in in mineral deposits, but the challenge is that mineral deposits are way more complex than petroleum systems. Right? Not that a petroleum geologist would like to hear it, but they are, right? And so that the challenges are being able to get the right framing of the mineral system, and you'll see different people have a very different thing in their mind when you say mineral system. And I'm not saying that that one that I put up is the answer, but I mean that's where we've come with it at the moment. So again, the systems thinking, I think, is the biggest thing. And that's clearly shown power in the petroleum side.
Thank you, Cam.